At no point in your rambling, incoherent response were you even close to anything that could be considered a rational thought. Everyone in this room is now dumber for having listened to it.
You lose! Good day, sir!
Hi, welcome to CheMistakes. Here we take actual student answers to questions and break down what's good and bad about them, how to improve them, and how to fully communicate everything that's going on in that chemistry question. Here we have a question about equilibrium. We're looking at butane going from the liquid to gaseous state. And what we're doing is, the question is, what effect would adding more of the liquid butane have as far as equilibrium position goes? So the student response to that is butane is added, the amount of reactants increases, which causes Q to decrease. To reestablish equilibrium, the reaction mixture will shift to the right, so the Q becomes equal to K. So the student here is doing a good job. They're talking about reaction quotient as the amount of products, or the concentration of products, compared to the concentration of reactants, with the appropriate exponents from the coefficients and all of that worked in. They give a good answer. They talk about how the reactants goes up, and so therefore the value of this goes up. That's in the denominator. Q is going to go down. That means that Q is going to be less than K, which means we have too much reactant, too little product, and therefore that's going to cause a shift to the right. Really, to improve this answer, we could get into a discussion on rates, the rate of the forward reaction, the rate of the reverse reaction. But really this answer is good except for one small thing that the student has missed. And that is that these concentrations of products and reactants don't apply to liquids and solids. So, and there's a reason for that, and that's a good opportunity for us to kind of tie in rates with this and explain why this doesn't change. But liquids and solids are omitted from your equilibrium expression, from your Q expression. So really, adding a liquid to this is not going to change anything at all. But let's go through and look at why that is before we just kind of accept this thing that we're told at the beginning of the unit. So if we were to look at a closed system, so we have a container here with some liquid butane in it. Okay, so we have some liquid particles in here, and then some of those particles are turning into the gaseous state. Whenever we're looking at equilibrium, or at least dynamic equilibrium, is defined as having opposing opposite rates that are equal. So we need to define what are our two rates that are going on here within this system. What's happening is the liquid is turning into the gas, and the gas is turning back into the liquid. So really, particles at the surface of this are escaping off into here when they get collided with in the correct fashion, causes them to turn into a gas. So we turn the liquid into a gas. And there's some rate at which that occurs, based on the temperature of everything, based on the amount of surface that we have, and based on what type of liquid it is. There's also a rate of the gas turning back into the liquid. That also depends on temperature. That also depends on what the substance is, and it also depends on the surface area. Okay? The larger the surface is, the more liquid is going to turn into a gas, and the more gas is going to turn into the liquid. So it turns out that it doesn't matter what shape of container you have, or anything besides what the chemical itself is and what the temperature is to affect the rate. So it turns out that if we took two containers like this, that the pressure of this gas and the pressure of this gas would be identical if we've established equilibrium. Okay. Now it turns out that if you then took this container and added more liquid to it, that the gas pressure in here would not shift from that, it wouldn't change. And if we think about why, what we're doing when we add this liquid, we're not changing the surface. We're not changing the surface area, the contact between the liquid and the gaseous state. Okay? So we're not changing how quickly the liquid turns into a gas, because if a liquid particle down here turns into a gas, it's just going to bump into things on its way out and slow back down and eventually return into like the amount of energy needed to stay as a liquid. It's only here where these transitions are occurring. Likewise, over here now, we're still seeing the same amount of particles turning into the liquid state from the gas because we have the same surface. Now, as this is going on, obviously if we were to change the temperature, that would affect the rates of these. But adding the liquid doesn't just change anything about how those rates will occur. Now the way we state that when we look at the equilibrium expression for this, so this equilibrium expression would just be equal to the concentration or the pressure of the butane in the gaseous state. And you'll often hear teachers say, well, you don't put solids or liquids, only aqueous or gas into the expression. Really, this is called an activity, but it's very similar to a concentration. Okay? It's kind of the concentration with no units. It's a simple way of looking at this. If you look at the concentration of a liquid, like a pure liquid, concentration is really a tough term to kind of define for that. So when we look at this, the concentration here, whether I have this much or this much, the amount of stuff I have in a given volume is the same. And so the concentration term doesn't really apply to this. So we often take it as 1 and then factor it in as a constant into the equilibrium constant. So in this particular question, if we go back then and look at the answer to this, a better way to say this would be that no shift occurs because adding a liquid will not affect anything from our reaction quotient. So our Q is going to stay the same because our Q in this case is just equivalent to the amount of gas. Sorry for the bad handwriting there. So adding a liquid doesn't change anything in our reaction quotient, and so we're not going to see a shift occur. Now, that's in terms of pressure at least, and that will work for the concentration as well. Now our space available changes, so our volume changes, so there's an amount of butane gas that will turn back into the liquid, but the final pressure and the final concentration of those are not going to change because of us adding a liquid to it. And then we would want to give a brief justification of saying that liquid concentrations are still constant regardless of amount, or that we're not changing the amount of surface, and so therefore our opposing rates aren't affected by this, and that's going to be sufficient for our answer for this.
Okay, a simple wrong would have done just fine, but